All right, to finish up on graph theory for data structures, we're going to talk about minimum spanning tree. This actually has a lot of uses. For example, a company needs to shut down a maximum number of connections and still be able to fly from one city to any other. So minimum spanning tree is basically a tree that spans. You can go from any point to another. Obviously, this one's over-connected because you can get rid of the connection between 1 and 3, and you can still fly from anywhere to 6 and 1, right? So the question is, how can we build this tree? Not tree, I'm sorry. Well, it is actually a tree. But how can we build the graph that has minimum spanning? Well, first off, there's actually multiple solutions to the problem. Are all these minimum spanning?
Yeah.
Yes.
Sure.
Yes.
Yes.
Sorry.
If you say it enough and confidently enough,
Yeah.
obviously,
Okay.
you're right.
I meant yes to.
Oh, wait, look, more definitions. A free tree is simple graph such that if U and V are two vertices, then they have a unique path from U to T. Okay, that's nice. AKA it's a tree. That's what we want. We want that such that there is only one unique path from U to V. There's nothing else. So you can't have multiple routes. I mean, that's what we're looking for. Rooted tree is which particular vertex is designated as the root. Sure. And the weighted tree is that you actually have weights assigned. Notice in our binary tree, we never assigned weights. Spanning tree is a subgraph. Whoa. Okay, all the vertices are still there, and there's a path from any to another. Yes, that's nice. The minimum spanning tree. Now, notice this is going to be different because there's multiple spanning trees, but the minimum spanning tree is the spanning tree with the minimum weight around it. So if we were to scroll back, which one of these is actually minimal? They should have different weights. 8, 15, 20, 25, 31, 33. What's this one? 10, 15, 21, 23. 28. So this one actually is less, or yeah, less. 2, 6, 13, 18, 23, 25. So this one's even less. So while these are spanning trees, this one is the minimal of the three. So we actually want the minimum one, the one with the least weight. There's two well-known algorithms to do this: Kruskalls and Prims. We are going to discuss Prims. And this one's fairly straightforward. We're going to talk about it. I'm not going to implement it in class. That will be your lab. And if you have some troubles, I'm sure there's plenty of internet research to help you out. But we want to build the tree iteratively by adding edges until a minimum spanning tree is obtained. So start with some vertex, don't really care which. At each iteration, add a new edge. That does not complete a cycle, add it to the tree. Okay, that's really it. Sounds fairly easy, but when you code this up, you're going to be using a lot of little data structures.
We're going to use the stuff we learned.
Whoa. Reminds me, I just saw the Honest trailer for Bill and Ted's Excellent Adventure.
Honest trailers are awesome.
Anyways, so we have our initial tree here. Notice that our minimum spanning tree contains we'll start with 0 and has no edges. And we have not visited 1, 2, 3, 4, 5, and 6. We're looking at 0. We have edges to 1, 2, and 3. So we choose the least one. Which one of those is the least? The lowest weight? From 0 to which edge has the lowest weight?
3.
Yeah, it has a weight of 2 going to vertex 3. So we're going to add 0 to 3 to our vertex. Vertices where we've visited are 0 and 3. We are going to add the edge 0, 3 to our graph so far. We're going to say we haven't visited 1, 2, 3 shouldn't be up there, 4, 5, and 6. And now, where can we visit? Well, we can still go from 0 to 1. We can go from 0 to 2. But now we can also go from 3 to 4. Which of those has the lowest weight?
3 to 4. No,
Has
0
a,
to 2.
yeah, 0 to 2. That has an 8. This one has a 5.
I thought that was 4. Oh, I see.
Okay. So we're going to choose that guy. Vertices now are, notice we have 0, 2, and 3. Edges we just have from 0 to 3, 0 to 2. Nodes we have not visited, 1, 4, 5, and 6. We again look at all the edges we have available. 0 to 1, weight of 6. We can go from 2 to 5, weight of 7. 2 to 6, which is weight of 5. And from 3 to 4, weight of 8. Which of those has the lowest weight?
2 to 6.
2 to 6. So we're going to add that edge. So we add 6 up here. We add the edge from 2 to 6. We still need to go to 1, 4, and 5. So here's our new graph. 0 to 1 is weight of 6. Let's see, 2 to 5, weight of 7. 3 to 4, weight of 8. And 6 to 1 is weight of 4. So which one's the least? 6 to 1, right. So that's going to add which node to our list?
6. 1.
1. We're adding 1 because we're already at 6. But we need to add 1. And that's going to add the edge 6 to 1 with a weight of 4. So there's 6 to 1. Our vertices are 0, 1, 2, 3, 6. We still need to go to 4 to 5. We can go from 1 to 4, weight of 2, because now we've gone to 1 from 6 over here. We can go from 2 to 5, right at that 7, and then 3 to 4. What is the least?
1 to 4.
1 to 4. Yeah, it's well labeled, isn't it? Which node is that adding? Our vertex? 4. So we're adding the vertex 4. Y'all okay?
Yeah. Just laughing at her.
Notice we add the edge 1 to 4. All we have left is 5. The only edges going to 5 are from, let's see, 2, weight of 7, and 4 to 5, weight of 10. Which is the least?
2 to 5.
2 to 5. So we add that edge in. Now we have all the nodes, all the vertices up there. We have no more nodes. We now have a minimum spanning tree. A minimal spanning tree. All right, when you go to approach this problem, the first thing you want to do is think about what data structures do you have? What are you holding each time?
A node.
A computer.
When you said that, my mind just went. No offense.
That was really funny.
All right, your vertices are a array, a list of vertices.
List of vertices.
Your edges are a list of
weights. Edges.
edges.
Whoa.
And the nodes you still need to visit are a list of nodes. So you got a list of nodes, aka integers, a list of edges, so you're going to have to come up with some edge idea, and then a list of nodes you still need left. All right, in order to compute this algorithm. Pulling it all together. Let's see, print. Wait a minute. Where's Prim's? Uh-oh.
You didn't add it. Just add it.
Oh my goodness. All right.
Or.
Oh, I can't wait. I can't wait, Jonah. Go ahead. Tell me. Whoa.
Is not.
I like it.
There we go.
Roll with
Wait,
it.
yeah, it is there.
This is not going to come out right. I can already tell. I'm going to paste this and it's going to look terrible. Oh, it didn't look that bad. Great.
Not as bad as it could have.
Returns the total weight of the minimum spanning tree with the given starting node. You must use Prim's minimal spanning tree algorithm. So this is just looking for the total weight at the end. So you can throw everything else away. I'm just looking for the total weight when you're done. You got it. Just throw it out.
Throw your computer.
Do a little animation like that. No problem.
All right. Any questions?
All of them.
All of them?
What's the answer like?
42.
So, graph with the JC list. Oh, this is lab 23. I'll have to update that for you.
Oh, you wrote
It's due a week from today. Everything else applies as usual. Any other questions, comments, screams of oxed?
What?
Sorry. I got that opportunity.
Arg.
Arg.
Ugh.
Insert.
Okay.
This is your last actual data structures lab.
Yes.
Next comes Bash.
Oh.
Great.
Right.
When do I get the hits?
Preferably right here enough to knock me out and send me to the hospital for like 3 weeks.
Okay, no.
Wow, that'd be terrible. Also, it's due in 2017, not 2016. I'll fix that momentarily. No other questions? Good. Well, good.